Today, what we're going to cover is the materials for the Markforged printer. Specifically, I'm looking at this from kind of a material science perspective. I want to know, being with a mechanical engineering background, I want to know what are my options, what's available, what are my limitations. A lot of these materials and a lot of these design capabilities are new. In fact, they didn't even exist or weren't even thought of back when I went through school. So what I want to see is what we can learn about the materials kind of as we go. And there are some handouts over on the side that I'm going to direct you to kind of as we go. So there's some additional information. Today, the main thing we're covering is information about the materials, you know, the considerations when choosing materials, compatibility with specific applications, some settings and print information, but we're not going to go into detail about how to use, you know, anything like that. It's mostly about sort of the decisions you make and how they affect the structural and compatibility nature of the part. We're not talking about how much printers cost, how to use them, any ROI calculations, design for additive manufacturing, how to service the machine. Those are all covered extensively in other areas. And if you have questions, we're happy to help you with that. But today I want to focus specifically on printing materials. We get a little bit of background out of the way just for reference, so we're all on the same page. There's three major categories of printers. There's the desktop series. It's a very compact, low-cost printer that prints composites and, depending on the level, can print fiber reinforcement. There's the industrial series, similar to the desktop series, does the composite with fiber reinforcement, but some of them have, for instance, cameras for monitoring. They have lasers for inspection and leveling, and there's some additional materials that you can start to expect from those. And then the last one is the Metal X, and it's kind of in a class of its own because it's a totally different technology. I mean, it uses a lot of the same stuff. There's a lot of overlap, but it's going to be a separate class. But we're going to kind of talk about it in parallel to the composite materials. Along with that, there's three categories of materials that we need to know about. There's the thermoplastic, which the desktop and the industrial series are printing primarily. That's the majority of the part is the thermoplastic. It's all based on nylon 6. So there's a couple different nylons. They're replacing tough nylon with nylon white, basically the same thing, just better compatibility. Then we have an ONYX material, which is just chopped carbon fiber along with nylon. In that thermoplastic, you have the option to add fiber reinforcement, strands of continuous fiber in either fiberglass, carbon fiber, or Kevlar, kind of embedded into the thermoplastic inside the part to give it additional strength. And then metal, completely separate, it's metal. Got quite a few different metal options, but it starts out as kind of metal matrix in wax and a binder, and then the process goes through and removes everything but the metal, leaving your final net part shape ready to roll. So let's kind of dig into each one just a bit more. Thermoplastic is a nylon 6. If you want to know more information about it, go look up nylon 6. That's it. That's what it is, right? So, like I said, they had a product called Tough Nylon or just nylon. They're discontinuing that for a new improved version called nylon white. The big thing is it's interchangeable. You can switch your machine over to use nylon from ONYX without having to replace any parts or do any major service. And it gives a better finish than the previous nylon did anyways. The ONYX is a mixture. So it's nylon, but with just fibers just kind of thrown into the nylon and mixed up. So they're all mixed in there. It's very much like a glass-filled plastic for those that do injection molding. And then there's variants of that ONYX. There's a fire resistant that's appropriate for like aerospace where it doesn't create noxious fumes and it self-extinguishes. They're looking at doing an electrostatic discharge one that conducts electricity. Really, really cool, but it's nylon thermoplastic. The supports are breakaway supports, so just kind of peel them off when you're done. You can do solid or sparse fill. Most of the rules of traditional 3D printing apply. You do want to keep your material spools dry before you print for the printing process, Water exposure afterwards, though, we're going to discuss later and kind of how that works. The fiber reinforcement. It's optional. You've got a lot of capabilities that you can, or ways and strategies to include the fiber reinforcement, but the fiber is actually embedded into the thermoplastic. You kind of think of it like, you take a soft material and you put like a rope on top, and then you take like an iron and you just shove it down, and you keep pushing until it melts the material underneath, and the material sort of embeds into the fibers of that rope, and it kind of makes it flat. It actually sticks it into the material. So all the layers are thermoplastic, but then along the way, you have the option to kind of squish in that thermoplastic or that fiber. And there's 4 main types. There's carbon fiber, very stiff, very strong, lightweight. It's the most expensive, but it's also by far the stiffest. If you're trying to replace a metal part, like an aluminum part, go with carbon fiber, you're going to get very similar properties. Fiberglass is a lot more cost effective. It's still very strong, but like I said, it's a lot cheaper. It's traditional fiberglass. There is a variant for high strength, high temp fiberglass that gives you some better performance, better stability at higher temperatures. And then there's a Kevlar, and of course Kevlar, everybody knows Kevlar from like bulletproof vests, anything that's impact heavy. So skateboard wheels, things that are going to get smashed up against something. Kevlar is going to make sure that thing does not degrade. It'll give a little bit, but it will not break easily. And then the metal X, it's metal. There's not much more to say. The materials are metal. So if you need metal, you can make them with the metal X. The process is really cool, though. And so I do want to kind of just briefly cover it, but the fundamental underlying process is not new. It's a sintered metal part. There's a couple things that are unique about the metal that are different from metal you would buy off the shelf. So for instance, it's 99.7% dense when it's done, meaning it's like a billet. It's not quite as good as a forging. It's much better. It's better than a casting, but it's a solid metal. The materials don't have any underlying grain orientation like you would with like a rolled metal or an extruded metal, where you've got an obvious grain orientation. It's completely isotropic. There's no z-axis direction, residual effect, or anything like that. The print is all metal, so the supports and the part are both metal, but to allow it for release, there's a ceramic material that you put in between. So when you finish printing, you've got metal with ceramic separating the supports from the part. Give it a tap and it breaks and it comes apart. But once the part's done, it's ready to use. Its final shape, its net shape, you can heat treat it, you can do anything you want with it. One thing that I've personally noticed, it seems like they're picking metals that are more difficult to machine. So they're either harder, tougher, exotic like titanium, and basically it's going to allow you to not only create these parts in a way that might even be better than machining for even production parts, but you'd have the ability to print even parts that are impossible to print using traditional methods. The hardware that is available today, it's been out for most of a year now, it's going to support all future materials. So there's some materials, quite a few materials in beta that are coming out soon. The software updates will allow you to know how to make those new materials in the future. You don't need to buy a new machine to support new materials. All right, so let's kind of talk a little bit about settings that you get to choose that are going to impact the final design. Material science, usually you don't think about the idea that, hey, I'm going to choose this part, but I'm only going to, put it in at a certain density. Like you pick a part and all of the properties of that part come along with it. They're sort of required. But with the Markforged printers, when you come in and you pick a part, like I've got a part here that I printed, it's a little display piece. You get to choose the material, right? So this is Eiger. This is the the interface that comes along with, it's included with the machine, and you choose the material, okay, but then you get to choose the reinforcement material, which is pretty amazing. It's going to change pretty substantially what you're going to see. Then you can come in and say, for example, I want to add brim or raise the part to try to give it more dimensional stability. I want to set the layer height, turn off fiberglass so I can get the opportunity to choose a layer height. Depending on the options you choose, that'll determine some other aspects down the line. And then you've got the fill. Do you want triangular, hexagonal, solid? I mean, these options have never really been available to us before. And so the choices you make are going to be a strong determination or determinant of the final material properties. You kind of, it's almost like you're in chemistry. You get to build the ingredients of the final part and the final material, where in the past, it's always just been, you want steel, you got steel and everything that goes along with it, and it's got to be solid because it's the only option you have. So if you want to learn more about Eiger and how those settings work, we do have an overview on Eiger available. But I wanted to kind of throw this out there that traditional material science is sort of being thrown on its head because we can do things that were never possible before. Let's get into the meat of this whole thing, though. The entire webinar, the main thing I wanted to accomplish was I wanted to make sure that we were able to answer the most common types of questions and address them generically for all the different materials that people have. So for example, temperature, right? This is a thermoplastic. As it gets hot, it starts to get soft. So what temperatures can we use it at? Well, the heat deflection temperature, and basically you just take a part, you try to bend it, and then you slowly heat it up. And once it starts to bend because it's soft, that temperature is called its heat deflection temperature. 44 to 50 degrees C, so 111 to 122. So for just straight nylon, as long as a human being is generally comfortable, then the nylon is going to be comfortable. If you need to go hotter than that, that's where you want to go to the ONYX. It's substantially more stable at high temperatures, up at 145 degrees C or 293 F. And if you do the ONYX with the high strength, high temp fiberglass, or even the ONYX flame resistant with the high strength, high temp fiberglass, you're up in the 150 C range, and you're getting some really, really strong, durable parts, even at some really high temperatures. So that's kind of where that operating range sits. For the thermal expansion, right, if temperature is your concern with respect to stability, the expansion of nylon is quite a bit higher than it is for things like metals, but the fibers are a lot less. And so you can see that, like ONYX, the nylon plus fiber is a fourth or less of the expansion coefficient of just straight nylon, because that carbon fiber is almost no expansion at all. It almost doesn't expand at all with temperature. So if you have temperature stability or thermal, stability is important, that's where you're going to want to add fiber to your part. Chemicals and fluids is another really big one. In the handouts on the webinar, there's a Markforged chemical resistivity chart. I pulled some of the ones that I thought were really interesting that don't provide any damage. Basically, they're rated as you might see a tiny bit of absorption or a tiny bit of expansion of the material, but it's no structural degradation, no problems at all for things like water, acetone, cutting fluid, diesel oil, freon, propane. It's pretty amazing, right? A lot of these solvents really don't affect this nylon and ONYX material at all, which is kind of unique among a lot of 3D printed materials. I did notice that it's fairly poor resistivity to a lot of acids, which isn't that big of a surprise. But these materials, or these fluids that you're likely to encounter, they're used heavily in things like CNC machining and robotics and stuff like that. And that's exactly where you see so much Markforged applications in things like automation and manufacturing. Chemicals and fluids, though, I did want to mention that moisture needs to stay away from the material before it's printed. Simply for the process of printing requires that the material is not absorbed a bunch of water. So there is a dry box with some desiccant to keep it dry, but after the printing, moisture is not a problem. And if you want to make sure to eliminate that moisture absorption, a very tiny amount of absorption, there is some sealing options that you can do. We'll talk about that kind of in the post-processing section. Another big one is UV exposure, which kind of goes along with radiation. So we don't have a specific test or certification that we can say, yeah, it passes this UV exposure, but we've had fantastic success with exterior applications where UV light is exposed quite a bit. So I expect great performance exterior-wise in terms of, temperature, weather, and UV light. It shouldn't affect ONYX parts. Kind of like tires are black because they have carbon in them for UV resistance. ONYX does the same thing. A nice little side effect is that ONYX and nylon are radio transparent, meaning the X-ray machines can see through the materials. So if you've got a cast, if you've got one of those halos or a brace that kind of helps fix a shattered bone or something like that, if you make it out of ONYX instead of a metal, you can then go image it with an X-ray machine. You can put it in an MRI because it's non-magnetic. So there's some really exciting, very structural applications in medical. We're not looking at things like inserting, into the human, although some of that might be going on. But for those structural designs, where it's really more of a mechanical design than anything else, we're seeing that a lot. So with strength, toughness, hardness, kind of a mechanical design, a mechanical engineer primary need, this is a really complex topic. And the more I looked at it and the more I studied it, I realized that it's a bit like, like a formula, like a chemicals, chemistry set. You get to build the material that you want out of various ingredients. So let's talk about the constituent components first. So stiffness. If you're worried about stiffness and deflection, nylon on the elastic modulus is about 1. ONYX is 1.4, so it's a decent amount stiffer. Carbon fiber is 54, ridiculously stiffer. So if you put in carbon fiber into your ONYX material, it's going to be extraordinarily stiff. Looking at aluminum with a reference of 69 versus 54 for carbon fiber, you're probably going to be very close to the stiffness of aluminum, but with a density that's a third or less of aluminum. So really awesome strength to weight ratio. Fiberglass and Kevlar aren't nearly as stiff as carbon fiber, but they do help out a lot. And then titanium and steel obviously are becoming much more stiff. When it comes to strength, however, that's where you see ONYX and nylon. Nylon theoretically has a higher strength, but because ONYX is stiffer, it seems stronger, right? And the nylon fibers might start to fail a little bit sooner because of that stiffness. So you get a little bit more toughness with the nylon. Toughness with Kevlar is also a big thing. So your toughness you're going to get when you stay away from the carbon fiber. But fiberglass, Kevlar, and carbon fiber are all going to give you a lot of really fantastic strength. And then for the metals, I can't really say anything about metals beyond what the metal alloy itself specifically is, because once you're done, it is that alloy. So 17-4 stainless steel, it's a very tough heat treatable metal, very chemical resistant, and it's weldable. A2 tool steel, extremely tough, heat resistant, or heat treatable anyways, great for things like cutting tools and dies. I'm thinking about making basically a knife, a custom knife out of A2 tool steel at some point. And then H13 tool steel is great for anything that's got to do thermal cycling. So, forging dies, injection molding, where it's going to constantly get really hot and then back to room temperature, or even really cold. Thermal cycling is not going to be a problem with fatigue on H13 tool steel. But those are publicly available materials. It's not unique to Markforged. In terms of stability and precision, it's another tough one to answer because it really does depend a lot on the shape. right? The way it's printed, whether it's printed by itself or with other parts so it has time to cool as it goes, they're all going to have a slight impact on the final result. Good rule of thumb though, for every inch of part, expect a precision of about 0.02 per inch. So a 6-inch part is probably going to have an overall length tolerance of about 12,000. Fiber helps that. There's other things that you can do to make that better, but really your best bet is to do what we call unit testing or benchmarking. Basically, if you think you're going to get there, but you're not sure, and you want to know more about what it's going to do, or you need to achieve a final result, you're going to have to probably print one, either the entire part or just that small feature, and print it. You can maybe print it in different sizes and different variations, and then measure them all and see which one gets you there. It's kind of one of those things where you can spend all your time predicting, but until you throw it on the machine and try it, you won't know exactly what it's going to do. But then once you run it, which is really simple and quick, you'll have a lot more information. In terms of just precision in general, the X7 has those in-process lasers. It can do in-process inspection of the part as you go. So with Blacksmith, which is coming very soon, it can even do artificial intelligence compensation. In other words, if the part is for whatever reason slightly drifting out of the tolerance range, it'll adjust its tool pathing on the print head to bring it back in and maintain the tight tolerance that you need. It'll print out reports on how it did, compensates the design as needed. It's got other design features that we expect to see that are just really cool. So X7 with the laser and the inspection as it goes is a great option for anybody that's going to be doing or requiring precision of their part. Post-processing is a common theme for pretty much all 3D printed parts. The better surface finish is always going to derive from the smaller layer height, but if you've ever seen one of the metal parts or one of the plastic parts, they're absolutely gorgeous. There's a little bit of roughness on the outside of the part, but a little bit of sanding, and this part down here at the bottom right, this is kind of I call it my precious because it's stainless steel, and I've been polishing the bottom of it, and I think it looks so cool. But basically, if you want a nice clean surface, you can sand it, you can tumble it, you can polish it. When it comes off the machine on the composites, there'll be a little bit of glue. Just wash that with warm soapy water. It's good to go. If you want to paint it, you can paint just about anything that's designed for plastic adhesion is going to do great. There's a nice blog on painting parts. And then water exposure or any fluid exposure, if you don't want any absorption, there's this Liquitex 395-0010. We would recommend that for sealing out anything from the exterior. Weight, that's going to be a potential concern. Obviously, the final part weight is going to be displayed as you go in Eiger. So whenever you choose a material and you choose your Sparse-Fill density and everything like that, that's going to be displayed real time. So you don't have to guess at what the effect is going to be or how it's going to do.
We're talking about weight. Relative densities, obviously your composites are all going to be pretty light. There's not a huge variation in density based on all the various composite materials. Steel and titanium and aluminum, obviously, everybody knows what those are. It is interesting, though, the Sparse-Fill percentage. So when you have a part and you want to do Sparse-Fill, how much can you expect it to get lighter? And the answer, generally speaking, can kind of fall within a range of values. The default Sparse-Fill is 37%. So 37% of the density is what the Sparse-Fill density is going to be. You have a range of values depending on the shape of Sparse-Fill that you want, and the number of layers and on the wall and on the floor are also going to determine what the final weight is going to be, but you do have a tremendous amount of control over the weight, even in the metal parts. But you're always going to be given that information real time in Eiger. One quick note though, I took a design and I tried to optimize it to make it look like an injection molded part. I made it kind of hollow and thought, well, that's going to help, right? By making it hollow like an injection molded part with thin walls, that was going to make it print faster and be lighter. And what I found was, is actually with these parts, it's almost better to leave it a big chunk, a big block, because the Sparse-Fill is so lightweight and yet still very strong that you can just make a big old chunky block and it ends up being lighter weight than the equivalent injection molded part with solid thin walls. So really cool. There's a lot of things that you learn kind of as you go through printing these parts. Let's see, material cost. That's another really big one. I'm not going to try to, quote you dollars per pound or anything like that, but I figured a long time ago that, if I could just relate it to my gut, right? I got a gut. I don't know if anybody's ever met me in person, but you know this about me. And I wanted to relate it to things that I could understand, so I related it to food. And I have this whole video on YouTube about pricing things out based on the size relative to food objects. And I picked a handful of different strategies for building the part and reinforcing the part. If I just look at just ONYX, an Oreo cookie printed in ONYX with the default materials for Sparse-Fill takes about 2 hours and costs about $1.70. So if you're trying to print a part and that part's about the size of 4 Oreos, it's probably going to take about 8 hours and cost, about $7-8. All right, so that's pretty good rule of thumb. A banana was 23 hours and $32. And then a loaf of bread, which was about as big as a metal part would go, that's why I use that, takes most of a week and about $250 in ONYX with that Sparse-Fill material. So hopefully, if you're trying to understand, okay, well, how much does that part cost? Well, it's not the same as what you'd cost to injection mold it in China if you were buying 1 million of them. And it's also not the same amount you would cost to sort of build a one-off prototype, from machining it or something like that, where you have to pay a huge premium just for the initial tooling of it. For print speed, you do have some control over this. Some things that do impact the time to print is the layer height, things like the amount of material you're using. So if you've got a part that has a lot of thickness to it, the Sparse-Fill percentage is high, there's a lot of support or brim that's done, it's going to take longer because it's just more material to lay down. And with that thicker material, you may also end up seeing a longer wash time with your metal parts. Things that don't impact the print time is the type of machine. The industrial versus the desktop, they're not printing substantially different speeds. The speed is set by what the material can be put down, reliably and with good finish. The material is not really going to change it. Carbon fiber doesn't print different than fiberglass. ONYX doesn't print faster than nylon. Steel doesn't print faster than Inconel. I mean, it's not really going to change it. Same with Sparse-Fill. If it's got more material, it'll take longer, but the shape itself is not going to be a big determination. And reasonable fiber usage usually adds very little to the amount of time. You do have some options for things like turbo print, where it speeds up in the Sparse-Fill areas because you don't worry about surface finish there. And turbo supports, which we don't usually recommend, or I don't recommend, just because there's a potential that the supports will be too thin and they might break. So it's a little risky, but it's available to speed up the printing of the supports. So that was the majority of what I wanted to cover today. There is a little bonus here. This is something that I've been working on, and I wanted to share with everybody that basically I wanted to analyze structural strength. I'm a simulation guy from SolidWorks, kind of, that's like my bread and butter, my background. And I wanted to know, okay, can I do finite element analysis on these parts? And forgive me, I'm going to breeze through this pretty quickly because I'm going to kind of give you the high-level summary rather than the specific mathematical derivations. But basically, as I tried to understand how to analyze Markforged parts, I realized they're very unique. They're a little bit similar to aircraft panels, where you have, a solid piece and then a honeycomb interior and then another solid piece, but you're not limited to just flat panels. So Those are hard enough to understand as they are in analysis. Add in the unlimited shapes and sizes and sparse fill percentages and material options and reinforcement options, and it's just unbelievably complicated what you can do. But you also can enclose the edges and do all kinds of other really cool things. The solid walls and the floors do put the material where it matters most, so the strength on Markforged parts is really awesome. It's a very efficient use, but the sparse fill, the stiffness of the sparse fill and the orientation of the sparse fill really has a lot to do with the overall behavior of the part. The continuous fiber filament is fantastic. It's perfect. We've got simplified approaches that we can use for traditional carbon fiber products, but because this is all kind of custom shapes and sizes and widths and everything else, it's a lot of complexity. And then you've got the z-axis differences. It's tough. So I thought, okay, I got 3 ideas for how you could analyze parts like this, and I can't get them all, but I thought I could get a lot of them. One is the basically brute force strength, which is just model the thing exactly as it's going to be printed. It's going to be a lot of mesh, a lot of really slow processing, but it should give us the most accurate result. And I was able to do that really quickly and well in SOLIDWORKS simulation. SOLIDWORKS 3D modeling does a nice job of helping me to quickly model that sparse fill. If you were to do an equivalent stiffness, basically fill it in with, I'm calling it like a goo. It's basically you've got solid material on the outside and then a softer sparse fill equivalent on the inside. You would be able to make a much coarser mesh, but it wouldn't necessarily give you the most accurate results. And it wouldn't do anything with filament, which is where you would have to basically do surface models, almost surface model slices, use shell meshes to try to account for the fiber layup and orientation, but even then it becomes very difficult. And if you try to make a part that's simple enough to run with these examples, you probably have kind of defeated the whole idea of using 3D printers, because they're amazing. You can make anything you want in these 3D printers. So this is the one I was hoping was going to work out, where you just make a solid material inside and just give it an equivalent stiffness. It should be a pretty conservative approach, and it should solve very quickly. And there's some really slick tools in SOLIDWORKS to just copy the body, shell it, do an intersect, and boom, you've got all your bodies ready to roll. The problem was, if you derive the effective material properties from like a little sub-study, you create a little mesh and analyze the mesh, and you say, okay, in this direction it's this stiff or this stiff, and that's an equivalent elastic modulus. You end up with material that's less stiff than it should be. So in other words, a 37% sparse fill can be up to 5 times softer than the solid material. And then directionality-wise, with 30-degree increments, you're seeing a pretty big range of differences depending on the orientation relative to the triangles. All that to say, it's complicated, right? So what I did is I created some equivalent elastic modulus parameters. I created some equivalent and calculated some equivalent Poisson's ratios and densities, and then ran it and tried to validate it, and I can calibrate these results pretty close, but they're never just consistent. It's never just like, oh, that's totally working. Oh, that was perfect. And every time I did it, it turned out that I would get close, but never completely there. And the more I dug in and tried to really optimize this, the more I realized, hold on, the scientific basis of failure, of material failure, is way more complicated for these parts than a normal part. Because when you look at stress concentrations, these two stress plots on the bottom here, those are theoretically the same part, but notice how much different the stress distribution is between them. And that's because of the nature of that sparse fill. It's just a really weird material in actual practice. And then, what does failure look like? If I see fatigue or buckling or cracking in that interior sparse fill, but the exterior shell stays intact, does that constitute failure? And the answer is I don't know. And so the more I did this, the more I looked at it, the more I realized I don't know what failure looks like, and it depends on what my application is. So I did all this really awesome, scientific, fantastic work, and I realized software is not really there yet. It's on its way. It's doing good. We've got some options, but because Sparse-Fill parts and continuous fiber filament parts are still relatively new technologies, they're not as robust as the others. So we're expecting to see some more things in the coming years to more directly do this without having to do long, complex workarounds. You shouldn't have to be an expert just to run a simple part, to see whether it's going to work. But there's another fundamental thing that this changes. It changes the equation of testing and prototyping. If you're sending a rocket to outer space, you need FEA, you need CFD, you need software to analyze it because you can't afford to fail. But with a 3D printer, you can print in almost no time at all and be testing very, very quickly a prototype and see if it works. And I did a webinar on this, on when to analyze using software, and it turns out the 3D printers are almost always in the hold my beer zone, which means, hey, let's just try it. Let's just print one and see what happens. And if it works, great. If it doesn't, we've learned something, and we can then adjust the sparse fill, we can reinforce, we can change the design, and you can iterate so quickly. So definitely, FEA is still important and it's necessary, but if you're going to 3D print a part, you have some advantages there that you don't have with typical manufacturing processes. That covers the majority of what I wanted to talk about today. We do have additional events coming up, Georgia, Oklahoma, and Texas coming up. We've got these printers actually in production down in our Dallas office, and we've got other printers kind of scattered around the country. We're going to be carrying them on road shows and stuff like that coming up. So definitely check out our new website. It's totally revamped, really awesome information up there, and the events specifically can be filtered by Markforged. And if you have questions, please let us know. We're here to help. We're here to answer any questions. We've got a lot of videos on our YouTube channel. Those handouts that are in this webinar are available. I really appreciate everybody's time today.